But in fact, the wireless communication could effectively work for about 80 days, which means the network was actually still up and operational, but the data wasn't valid anymore. But ironically, when we put 4 modes, we call them modes, the mode's a sensor node, and we put them in a network, and we don't know why this is, we actually can only get about 13 to 15 days of operation. That's without any solar panels. That means with rechargeable batteries running. Actually, the 15 days is for non-rechargeable, and 13 is for rechargeable. That's why we have this discrepancy between the two. So that tells you we're lucky if we can run 2 weeks with the way these things are. And so power management is extremely important in these units, unless you're going to plug it to the wall, right? And then you're happy, no problems. Okay, so we started in the summer of 2008. We actually got some prototype put together, very similar to what I'm sending around. And we actually put them on the rooftop of our university. We were afraid people would steal them and things, so the rooftop is kind of has doors locked. But they have actually an atrium up there, so it's quite nice. Lay them all out. We wanted to know how they would operate in that environment. And we found some neat things, like some leaked, and that's about design by engineering, bit building. But anything, what we found was that topology changed quite often. And what I mean topology is what happens in the CTP, the connection that occurs. Actually, in this example, the radio receiver, the gateway is in here. It's actually behind this window, and the rest of them outside. So actually, our receiver is not weatherproof over this side. You can see actually there's a laptop can there because we experimented at the time. Obviously, it doesn't stay there. And there's about 7 of these on the roof, and they create a topology. So here's a topology as an example. Here's a glass window. Here was the node 0 is always the receiver in this protocol, and these were all the nodes IDs that we had. And you can see this was roughly 45 feet across and about 50 feet wide, a very large area. And this is actually a topology. These 14 would decide to connect to 19. And what we found is these flipped around a lot, which they shouldn't, but they do. So the topology's flipped. These guys would go to 17, sometimes 19. So whatever time you looked at it, this topology was flipping around the place. That's actually bad sometimes because it means that there's a lot more communications occurring that is not focused on transmitting data, but actually on keeping this topology active. But what we found is that wireless is very sensitive to shadowing. It's extremely sensitive to shadowing. It's actually very unpredictable. And what we found is an example of an experiment we did. If you take a radio like this, originally, the original design didn't have this external antenna, it had an internal antenna. So that's why it's laying down like this in the box. And you flip the box around, and then you measure how far the range is, that you can measure the maximum range before you stop getting transmission. You can see that actually there's large changes. You can go 126 meters, it's actually meters in this case, and you can go as far down as 64 if you're in this configuration. So that varies a lot. And you can see even from other nodes, you get discrepancies. This one, for example, is 141 here, larger than 99, and this one's flipped over. So every radio is unique to some degree. And the main problem is if you take this thing and flip it this way, the electronics in the back cause a shadowing, they cause a blocking of the signal transmission. So when we first set them up in the field, this is actually our second deployment, set them up in the field. These are now calibrated. Now we're capturing real data. We had a real problem getting them to talk to each other, even though they were only maybe, like I say, 30 meters apart, because they were being shadowed by electronics that were in the back of here. So that means that was like going through, basically that signal was being absorbed by the electronic circuits, is what was happening. It's probably a little hard. You'll see more diagrams here, but yeah, this is a little bit dark. I just want to show you that what we did was put it in a head on to try to kind of get this feeling of a dip, right, which was our original goal in the project. There are 10 sensors, 10 nodes here, 4 sensors on each node, that's 40 sensors. And this is a better close-up. There's one here, there's one here. We found any piece of pole we could grab onto and whipped it on there. And in fact, that was interesting too, because if it was really windy, which it is all the time there, it just shakes them, and we have to make sure to bolt it down really good. Otherwise, the electronics come apart. So this is actually a configuration diagram. Here's the pond. The actual node is in my office that collected the data. So again, it was behind a window. It's an Ethernet gateway. So it actually collects the data, shows it into an Ethernet port. And these are two new, I had to actually survey these in. I did them manually because we went around with a GPS, and the GPS is really not very good. We had actually manual GPS. I don't know what quality it was. It was nice to see the presentation of our GPS. But we couldn't get elevation very well. That was one of the main problems, the GPS. So when we took the GPS values and put them on here, they were just, it just didn't reflect really the position of those sensors to any degree of accuracy. So we measured these in. I took a transit. I took a survey course back in my undergrad, whipped it around and did that in the afternoon. So these are actually properly positioned, and these are node IDs. Some nodes don't have sensors. I have to check and see which ones they are. Some of them actually, some students actually got drunk one night, I think, and they cut them off. So they have like one that's like dead pretty well now in terms of temperature. But that's what happens. You know, they're out there, they're fastened on, so we know which ones don't give us some data. Okay. So you see a better picture here. The whole idea was that we built, here's a radio, and we put a sensor up on top, about 2 meters up in height, and then we try to put this on as low as possible to see if we could measure differentials between upper and lower distances. The other thing that we did was we put 2 transducers in here and 2 in there. The reason behind that is we wanted to know how well the temperature sensors themselves were working, and that worked out quite well. In fact, the transducers worked really well. We had no problems with those. These transducers would measure the same temperature, and these 2 here would measure the same temperature quite often. I think actually most of the time, unless we had a bad cable connection. The resolution of the sensors are 1 degree, so we can't go better than 1 degree. If we get half a degree, then we know we're within 1 degree anyway. And then we could measure the temperature difference in here, which is the objective of the project. And then we also compared the temperatures across all the sensors, right? So that we could get a sense whether there was a discrepancy. Now we used the k-means outlier algorithm, and that algorithm allows us to determine, again, if sensor data is off kilter or not, and also allows us to view that, in fact, if you compare a bunch of sensor data together, you may get an outlier that's a real outlier, right? Which means you are really detecting a strange reading. But the only way to validate that is to validate against more sensors to see, hey, okay, 10 of them are saying that they're off the same as the other one, so therefore it's not really a bad reading. So that's something you have to be careful about. So this is a sense of the type of data we received. This is over 12 hours on October 2009. So these actually we kept running all through the winter, and we have data acquired around those periods of time. So we started in the fall putting these up in the field, and you see early in night that there is a temperature difference between top and bottom, and later during the day. I have to apologize to my students got time sampling, but I've got to tell them to put hours down. So you have to kind of guess that that's like a quarter of the way in 12 hours. And then you start getting rise in temperature as the day progresses, right? Which is kind of typical of what should happen. And we do plot. So, for example, between the sensors, we do plot, for example, the difference between top and bottom. And here's the difference between top and bottom. So where we start getting significant differences, then we know there's there's a change in temperature, and then it goes down. It's funny, they all have this type of characteristic. During the day, they seem to come together. I looked at a lot of the data, and at night they seem to separate. Which I'm not my background is software and distributed systems, so I can't comment on why that is. So for example, here's another one, another sensor, similar pattern, but we see later a convergence, and we see this big spike. I think that Mike had alluded to has also occurred. We don't have as many fluctuations as he does. I think because we don't have foliage really, we have open area. We have a lot of wind there. It's really windy in that area, so we don't see that type of fluctuations that are occurring quite a bit that he saw. Also, also think his sensors are a little bit more sensitive